can't even see. I think we're good. All right, we're going to go. Hi, everybody. Thanks for coming to me for the very first session of NDC Oslo. There was a lot of other things to see, so I appreciate you coming to see me. This is like my 5th or 6th time here, and not since before the pandemic, and so it's awesome to be back. This talk today is about modern web applications and how we can go about making them more observable. And when I say observable, I mean like the monitoring-y kind of buzzword around observability, the degree at which we can understand what things are going on. Not like the JavaScript pattern around observable objects or that sort of thing, just to clarify. And if you did think it was about that, I won't cry, maybe a little, but I'll try not to cry if you get up and leave. So when I say the word observability, here is what I think that means. Because the term is still fairly new, and if you ask 10 different people, I think you're going to get 10 slightly different variations on what does that word mean. I think what it means is, because it's one of those ILIT keywords, it's the degree to which, or your maturity in, knowing the state, performance, behavior of your system without necessarily, or without stopping it. So we're not turning things off and attaching debuggers. We're seeing, hey, how is our web app running right now? How is it going fast? Is it not throwing any errors? Are the users having a good experience? Are we accomplishing the business goal that we set out to accomplish by building this thing in the first place? In many ways, personally, this is what I always considered monitoring to be, but I guess the industry collectively has defined it as something bigger than that. And this seems like a pretty good thing for us to have. But how do we apply this idea specifically to web applications? Usually when people are talking about observability, it's in the context of like DevOps, cloud infrastructures. Do you hear that? That's not cool. So the analogy for this talk, and web applications in general, is icebergs. I like icebergs, and I can draw some pretty pictures of icebergs. Icebergs, like web applications, come in lots of different shapes and sizes. Some of them are very small, like this one. This is one of my favorite small web applications. I encourage you to go visit it later. It's by Lemon, who is also speaking in this time slot, but it's a website called party.party. So party is a top-level domain, and there's 4parties.party. And it's a really silly website that looks a little bit like this. This is one big yellow button that you push as many times as you can and accelerate the party meter. That's it. That's the whole thing. This is a small web app. One developer can and did build this. They can understand how it works. They know everything about it. They can decide what is the appropriate level of observability to add to it. But like icebergs, some web applications are huge. This is a retailer in the area that I'm from called Target.com. And Target is probably the favorite pastime of people in the state where I'm from. But it's also this huge retailer that you buy everything from. Everything from groceries to housewares to diapers to beer to everything. It's so big that one developer cannot possibly hope to understand how it all works. It does coupons, it does product, it does sales, it does this weird data analysis stuff that can tell whether or not you're pregnant before you know and send you mailers with coupons for diapers, which is some of the stuff that they actually can do, which is a little creepy. But regardless of what size web application you work on, they're not easy to work with. They can be treacherous. They can do all kinds of terrible things. And web applications can break in unpredictable ways. Lots of subtle bugs and cracks where they fall apart. Only 1/8 of an iceberg is visible above the water. And so the ratio of a front-end code to back-end code might be a little different than that. I think all of our applications that we work on have a mix of some of the code that we write is above the waves and some of it is below. When most companies think about observability and they generally focus below the water level. We're looking at the services, the databases, the cloud systems that we are monitoring. Their platforms, performance, activities, tracing the calls, and understanding the dependencies between things. And that's all super important. But ultimately, the user doesn't care about any of that. The user doesn't care if your cloud service is online. The user doesn't care if your database is running out of space. All they care about is whether or not the button works on the UI, where they can do their thing, where they can accomplish the thing that they set out to do. The users only care about the website. It's the culmination of all of the work that all of our systems below the waterline do. And like it or not, it's the only thing that our users really care about. The search button is throwing an error, not your inventory service is offline. And because of that, because our users really only care about this, the web tends to be this triage point for large organizations. Who works in a company where you have like separate engineering teams for the front end and the back end code? Anybody work at a company like that? A couple? I've worked at a bunch of companies like that, and as somebody who usually works on the front end team, I'm always the triage point. When something's broken, I get a ticket to go fix it. Even though it's not my fault, it's this API changed or your service is offline. That's not what triggered the problem. The problem was triggered by something in the back end and observed from the front end. So most of these DevOps tools tend to observe their systems from below, but that's not how our users care about it. It's really important when we choose to look at a system that we choose where to look at it from. What's our perspective when we're monitoring the system? And so I want to tell you a story about a real system that I built a few years ago and how this kind of problem was particularly called out. So I was building a system, and it was a client server. There was a rich web app built in Angular and a bunch of services that we called to do the thing that we needed to do. And I needed to make sure, it was my first time using this cloud, and I needed to make sure that those services were online. I didn't fully trust it. So I built a little agent, a little bit of code that says, hey, I want you to call my services periodically and just make sure everything is good. Make sure all the downstream things are working, everything's great. The problem that, of course, we ran into is inevitably, we ran into a case where the services were offline to the client, but our agent thought everything was fine. How many times has AWS gone down, but their status page been all green and everything looks fantastic? Too often. And in this case, the agent was sitting inside the same infrastructure that I was monitoring. And so yeah, if you happen to be inside the cloud, you could call the cloud just fine. No users could call it, and so that ultimately, this didn't add any value. So we moved the agent out into a different cloud, okay? So we're like, all right, we're gonna host our service in cloud A, and we're gonna monitor it from cloud B and cloud C. Now we'll know. Now we'll know that this thing works. All three regions can't go down at the same time, can they? Well, no, but those clouds are connected to each other via different networks than how most users connect. And often, the clouds will be able to talk to each other, even though an end user can't. And so we would still run into cases where important clients were unable to talk to our systems, even though all of our agents were reporting green, which is embarrassing. So inevitably, or eventually, we decided to move the agent into the client itself. I wanted to know when my actual clients couldn't talk to the service. But where do I send that to? Like, if my clients can't talk to the service, it can't report to me via the services that it's offline. And so we decided to just we bought a box and stuck it under somebody's desk. And it was like the emergency, hey, everything is down and clients can't talk to it box. And it's super unlikely for a major cloud provider and a box under Eric's desk to both go down at the same time. So because of these things, because the client side is paramount of importance to the user, and the client side being this triage point for the problems, not only should client-side concerns, client-side monitoring be part of your monitoring and observability efforts, I argue that it is the most important thing you should monitor. It is the first thing you should monitor. If you're only going to monitor one thing, you should monitor what the user is looking at, not what you as engineers are looking at. So that was my long preamble about why I think this is super important. Why do I think that we should spend time observing the client side, and why I think that is the most important thing to look at. And so we're going to look at 5 things today. First, just to level set, we're going to briefly talk about the architecture of a web application, just so that we're all on the same page. Then we're going to look at exception and error tracking, performance monitoring, and usage analytics, which are these 3 really important common set of tools for monitoring client-side applications and how they interact together to give us better observability. And finally, we'll talk about the limitations that we deal with in the client side. Does that sound good? Great. So who am I? My name's Todd. I'm what you would call a full iceberg developer. I do all kinds of different stuff. I'm from a town called Stillwater in Minnesota in the United States. If you know me from other things, it's probably this. I built a thing called Track.js, which is a JavaScript error monitoring tool. I've been to NDC many times talking about it. It's pretty cool. Since I was here last time, I started building the second thing called Request Metrics, which does some performance reporting. And I also run a thing called PubConf, which we are hosting one of those here on Saturday night at the Scotsman. Basically, I pull in 5 to 10 of the most entertaining tech speakers I can, and I bring them to the bar, and I say, hey, you have 5 minutes to make people laugh. And that's what we do. Lastly, before I start digging into the meat, all of these presentations that I do evolve and grow over time. So if you see something you like, please take a photo of it, tweet it out, share it, so I know, hey, these are points that people enjoy. It helps promote me, and it helps promote this event, and show off to all your coworkers, hey, look at all this stuff that we're doing here without you. So let's talk about the architecture of a web application. How many of you in the room today are developers? Almost everybody. Who are like analysts, product managers, non-technical but still work heavily with the web? No way, this is all engineers. Cool. So we don't need to talk about this in a lot of depth. So if you build a lot of web services, you might think you have like microservices and hundreds or thousands of services. But if you're building a web app, you almost always have more instances of the client side than you will ever have services. Every single user is its own instance of your client-side application, entirely responsible for the end user experience of exactly one of your users. And for that user, they might be running on big hardware on fast networks, or they might be running on an old Android phone in a train. But they all have the same general structure. The client environment is the browser. That is the runtime. Everything we do is managed by it, limited by it, and run by it. We create in the browser, we create HTML elements and styling and animations and clicks and transitions and all of those fun things that make up a modern web experience. We add the UI on top of the browser. And we have a network. Things like fetch, XHR, JSONP, WebSockets, all of those things that we use to execute actions and get data. And in many ways, what our web applications all do is use JavaScript to glue these two things together in a super simple description. We take UI events, we attach them to network events, and vice versa. And we can even reach out to other client-side applications, embedding third parties, application code, iframes, even direct socket connections. These are the super big components. Any one of them can crack and cause problems if we don't watch. Our application code runs JavaScript. JavaScript is not always the easiest language. Async execution, understanding the functional context, and evolving syntax make it really hard to write JavaScript and have no errors. Errors are inevitable in most software, and JavaScript specifically, even for the most disciplined of us. Networks. Networks are super volatile. Networks are way more volatile than you imagine until you start actually monitoring them and seeing how often they go down, how often they manipulate things. Many end users connect through networks that are not always reliable, are slow, they drop data, and it's not always all or nothing. When I first started monitoring my applications, I would think, oh, a site is either up or it's down. The network is either green or it's red. And it's not the case. There's lots of times when a website can load 2/3 of the way, that 2/3 of your scripts will load, and one of them will not, leaving the user in a weird state where they submit a credit card form, does it actually post where it's supposed to, or did the JavaScript that was supposed to intercept that fail? Third-party code is built into most of our web apps, and sometimes third parties go offline, mostly without giving you notice. And when our integrations with those third parties go down, does our app know how to fall back gracefully? Users, software would be so much easier without all of our users. Sometimes users will do odd or unexpected things in the web browser. They'll install plugins, they'll install extensions that change what things are going on, even intercept data and manipulate it. They might even install plugins that, like, in their desperate attempt to get a discount on buying something online, will inject code into every page that they visit. And browser bugs themselves happen, but they are rare. More likely, there's just a known browser incompatibility. I know most people think, hey, we're basically all running on Chrome at this point, but there are still 5 major browser implementations surfing the web today. And each of them have subtle, documented differences in their API. The spec is not consistent everywhere. I have 4 open bugs in different browser clients today. So we have this complicated environment of millions and millions of clients that can break in unpredictable ways. But this environment is also paramount to our users. This is the most important thing to them. So what do we do? Let's dig into these 3 core areas of web app observability. First, let's talk about error tracking. So let's define it, so we're all talking about the same thing. When I say error tracking, I mean recording those exceptional states. Something is not as it should be. Those exceptional states in the UI, network, application code, or browser that make up our client-side experience. The client side is, as many have described, the most hostile development environment imaginable. Errors are going to happen. Recording them and their trends allows us to understand the resiliency in our code. And so to discuss error tracking and all of our other client-side observability, I need a practical example. And so here is a little website that I enjoy a lot. I am not actually involved in the construction of it. I just happen to know some things about how it was built. This is Minnesota Pure Clear, and they make ice. Not just any ice. They make really, really good ice. You know those giant ice cubes that they put in, like, expensive cocktails? You know, water it all down, but like the ice is so clear you don't even know that it's in the glass. This is one of the companies that makes those. Their application operates both above and below the waterline, both client-side and server-side. Above the water, we have 3 core pages that make up this site. There's a shopping cart, a product page, and a checkout page. And below the waterline, they call 3 main services: a customer service, a product service, and an order service. This is how the thing is basically put together. There's even a third-party integration where they call it to Stripe for processing credit cards. It's a client-side integration that just uses JavaScript to pass out a token and return, whether or not it was accepted. So how can we use error tracking to better understand Minnesota ice? Let's look at some ways that this particular architecture is likely to break, and some ways that it in fact did break. Here's an error that we would expect from their architecture. Stripe checkout is not defined. So the stripe checkout not defined happening on the checkout page. And it's happening almost right after a page is loaded. If we were to look at that source code, we trace, what's on line 1, column 445, and we would see code that looks a little bit like this, where we're loading a script file from Stripe, and then in the very next script block, we're calling stripe.configure with their key of some kind. But what would happen if Stripe is down? If the call to js.stripe.com fails, which it could for any number of reasons, but if it fails, then on the very next line, when it calls stripe.configure, Stripe is not defined. And therefore, it would start throwing errors. And JavaScript blows up because that Stripe checkout is not defined. Now, why would it not be there? Well, Stripe could be down. That's not super likely, but it could be down. More likely, the actual client failed to make that call because this is the first time it's doing a DNS lookup on stripe.com, or it failed to make an SSL handshake, or the network dropped periodically. They roamed from one tower to the next or something like that as they were loading this page. But these are all things that are super likely to happen for some of your users. This particular error impacts the checkout page and would prevent them from giving us money, which is kind of the whole point of having this website. Services, especially third-party services, are never going to be 100% reliable. And we found a bug here because they didn't have a graceful fallback. We need to expect that that third party is going to fail some percentage of the time. And what should we show the users when it does? Probably not a broken form. Let's look at another example. Here's another super common runtime error. It's an error that I, in fact, usually have run into at just about every application I've ever worked on. Minnesota Ice had this error on the shopping cart page. Unexpected token angle bracket. And if we were able to trace that, it looks like it comes right before a call to a network request out to the customer API, which was returning a 503. Well, if we look at the code, we would see something like this. For the JavaScript developers in the room, this is, I know, the old style of it. This isn't fetch. It just shows off the example a little bit better. This is building up an XML HTTP request. Hey, we're going to make an AJAX call, and we're saying, hey, when this thing loads, we want to parse it out, and then go ahead and fire the call. And so we get this response back, and we expect it's JSON, and so we pass it into json.parse. And this is what's blowing up. So how could this problem happen? Does anybody know? You got HTML back. You got a page like this from your service, which happens if, we're usually fronting our services with some sort of web load balancer or something like that. And when that's misconfigured, or when something is just down, it's going to throw an error. It's going to return a page just like this, which looks a lot like that in the actual markup. And so we're expecting to get back this JSON response back from our JSON API, but instead we get this and the whole thing blows up. So this is another very common bug that impacted an important bit of UI, and it showed us that we don't gracefully handle our API calls. As somebody who works on a client-side team a lot and interacts with a server-side team, I can't trust the server-side team to give me back what they said they're going to give me back all the time. I need to make sure that I'm properly catching that. If I get back crap from the backend API, I need to catch that I got that crap and show the user some sort of graceful fallback and notify me so I know to go and figure out what's going on. The service itself is not the only part of the component that has to be watched. We have to look at all of these intermediary web layers. So error tracking gives us a better perspective into the completeness of our web application. It can show us these sort of problems when they happen in real time. It can show us things like browser incompatibilities and logical bugs and third-party service failures. Any of these things that can blow up the page can be caught by error tracking. And it gives us this real-time and historical view of how to get it. But how do we get this data? How do we pull this data out of the browser? We need to understand how error tracking plugs into the web. And we do this by putting some sort of an agent in your application. So you have some part of your app, some part of your web app that is now responsible for errors, that it can catch those errors when they happen and know what to do with them. Unfortunately, the web does not have a unified way of revealing errors. No one could have ever imagined that a language designed in 10 days could throw an error. And so it's just not built into the system in a consistent way. There is a global exception handler, like, hey, something blew up, but it doesn't actually catch all kinds of errors. It only catches like 60% of errors. There's a bunch of other things that can go wrong that don't end up there. There could be globally rejected promises. There could be console errors. There could be failed network requests. There could be 6 different kinds of errors thrown on the web that come in from different places. And because error tracking doesn't plug in super easily, the agent needs to be a little bit smarter. This isn't just about listening to a global on-air handler. We got to plug in a bunch of places. And so how do we do that? Well, JavaScript is a fun language that lets us redefine things like this. Here's one way that we can capture a class of errors from the web. And this is a process where we are going to override console.error. A lot of libraries still reveal errors simply by calling console.error. They don't throw something, they just say, hey, an error happened. And we need to know when it did so that we can capture that context. And so what this bit of code is doing is we are grabbing a reference to the original window.console.error function. We're taking that function and we are saving it in our own variable. And then we're just redefining it. There's nothing saying that we can't just redefine what these core functions are. And so we just say, hey, console.error is this new function I'm making that takes some number of properties that we're going to call messages. And when we get those, we're going to throw an error, or we're going to create a new actual error object with it, because we want to be consistent about how we're going to reveal errors. We're going to try and mask that. And we're going to send it off to our servers. And then we're going to call that original error function. This is one of the few ways that you can call a function in JavaScript. We are going to apply, which lets us set the value of this, and then we're going to pass through those original messages. So this is a way that we can basically instrument a function. We can redefine a base level function in our JavaScript app to do something new. We're going to grab any time console.error is called and send it off to our servers. And this is how a lot of JavaScript agent code works. It's by intercepting these different things, either to understand context of when are things called, to understand how often a particular function is called, or to grab context when an error is about to be thrown. When something exceptional happens, we need to take that code and send it off for analysis. But often, browser errors themselves, even if we can capture errors from all these places, are hard to understand. JavaScript code runs asynchronously, minified and detached from the sources we wrote. It often does not look anything like our source code. So error tracking needs to be a little bit smarter, because it's really hard to get an error report like this and know what's going on. I really, really do not want to look at that scripts.js file and figure out what's on line 1, column 5,308,563. That sounds like the worst afternoon ever to figure out what is actually going wrong. So instead, we want to look at context. What kind of things are going on? And so when you're building out an agent, understanding what is the state the system is in when an error is thrown is really important and can help you avoid having to do things like this. So when we implement that send error function, we want to be able to add some metadata to it. So in that earlier example, we would call send error with some sort of error object, and maybe we want to enrich that. somehow. We want to say, okay, give me the state that my application is in. What's the state of the form? What's the state of the component? Whatever. Tell me about the user, who's currently logged in, and what's their session information. Maybe things like what network requests have recently been fired off, or what other things got put into the console. We're still in the browser, and so there's lots of other context that we can just grab about what browser is running, how big the window is, cool stuff like that, depending on what your app does and what your kind of users are, would be interesting for you to grab and include with your errors. But right now, that error is still in the browser, and so we need to send it somewhere. It's got to get out of the browser so it's somewhere our developers can actually look at it. So once you have an agent observing errors in your app, you need to send it off. So this could often be some sort of logging and metrics API, a logging service that you build into your stack somewhere. I've built this many times. You could build this like a specialty API and store it somewhere. Elastic and Kibana are fantastic tools that a lot of people use for this. This is a screenshot of a Kibana dashboard that I use for capturing logs out of one of the systems I maintain. And it's super interesting. It lets me do a lot of analytics about what's going on and reporting on when things blow up. But it takes a lot of time to build. It takes a lot of time to figure out the data structure behind that. Or alternatively, there's a lot of third parties that do this. I happen to make one of them that I think is pretty cool, but I might be biased with it. It handles a lot of that stuff for you and shows impact analysis and error context and stuff like that. It's pretty opinionated on what it shows you, so it's not as generic as Kibana, but we think it's interesting. Okay. Error tracking tells us when our applications and components and APIs fail. But maybe all our applications are working, no exceptions are being thrown, but they're just running a little bit slower than we'd like them to. How do we know? Well, we'll turn to performance monitoring to answer that question. And when I say performance monitoring, here's what I mean. Measuring the user perceived timings of those network transmissions, user flows, and functions through our app. How fast is the user getting through the checkout flow? How fast does the checkout page load? How much does it shift around? There's lots of different ways that we could think about performance. The most important metric that most people think about when it comes to web performance is page load, which is just the time it takes from when the user clicked on a link or navigated to a URL or went somewhere until the time that the JavaScript load event fired. This was how we measured performance for a very long time. And it's still a useful measure today. But a lot of organizations, and Google generally on the web, started thinking about page load as a way to incentivize and objectively measure pages. And as soon as that happened, it became real easy to game the page load metric. We could just return an empty HTML document and load everything asynchronously, and we could have a really, really fast page load measurement, and the site feels slow to everybody. So recently, Google has decided that there's new ways that they want to measure performance on the web. And they have released these metrics to us all, called the Core Web Vitals. How many of you have heard of Google's Core Web Vital metrics? A few of you, good. These are super important, but they're a little weird because there's lots of different ways performance on the web can be measured. They can be measured as, each of these is currently on the standard track to become an official API, but right now they're all just part of Chrome. But you do get these measurements whenever you run a Lighthouse report or a page speed score, and it's particularly important to understand these now because as of March of this year, your Core Web Vital measurements have been recorded by Google in anybody who visits your site with Chrome, and they are impacting search results. This is now part of the PageRank algorithm. So if you have a slow website, you are losing PageRank score against competitors who are faster than you. That's super important. So the 4 things that we're measuring here are a little weird. The first one is FCP, first contentful paint. And this is the time it takes between when the page is first, or when you first start navigation until the first bit of content is shown. It doesn't matter what that content is, just something has rendered on the screen. The background color has changed, there's some header text, something. Just the time it takes for something to happen. And it's telling the user that, like, hey, the server will fulfill your request eventually. We are going to respond to you. And Google thinks that you need to respond in less than 1 second. In 1 second, you need to show the user something, or you will be penalized, which is super fast. Actually, I think they recently changed that to 1.4 seconds. But that's still super fast in order to respond quickly. The next one is LCP, or largest contentful paint. That is, how long does it take for the largest bit of content to be shown? It doesn't know necessarily what the most important content on your page is. But so we're going to use a proxy of whatever's the largest thing. So the hero image, the video, the product image, whatever the biggest, most striking thing on your page is, it records the time it took to render that. How quickly can you actually show that? And that needs to be done in 2.5 seconds or less. I'm going to skip to the 4th one and talk about FID, or first input delay. First input delay is basically measuring how much JavaScript are you putting on the page. It is a measurement of between the user's first interaction on your page, the first time they scroll or they click or they do something, until the browser can figure out what part of your JavaScript should I call to respond to that event. It's not a measurement of how long your JavaScript takes. It's just a measurement of how long the browser takes to figure out what the heck it needs to do with the blob of JavaScript you gave it. So if you download 2 megs of JavaScript that the browser now has to parse and figure out where to bind events to, it's just going to take too long for it to figure it out. So this is both a measure of how much JavaScript you're putting down and is it an appropriate amount for the capability of the clients that are visiting your page. Because if you have slow devices that can't load the JavaScript you're running, this is still going to take too long. Because this has to respond in 100 milliseconds or less. The last one is cumulative layout shift. And this one is a little hard to understand. It's a measurement of how much did the page move around as it loaded. So as content loaded asynchronously, did it get pushed around? Did things move around on the page? And so here's an illustration of that. Here's like a simple mobile app, and I want to click this button to do something awesome, but every time I'm about to click it, this annoying ad kind of jumps in, and it causes a layout shift to push it down. A lot of sites might do this intentionally in a nasty kind of anti-pattern to get more advertising clicks. I also built a little fun little game that you might want to play later at shifty.site to illustrate this concept. And it's this e-commerce retailer that you're trying to get the deal of the day, but things keep loading asynchronously and pushing around. And so it's how many deal of the days can you get in 30 seconds? My record is 9. But so this is a measurement of how much things are moving around the page, and it's both and it's in total, cumulative. So as everything is moving around the page, it's counting up how much movement is happening. And it's not exactly a percentage. Somebody at Google corrected me once when I said that it's a percentage. It's a score, but you can kind of think of it like that because 10% or 0.1 is the maximum value that you're allowed before you start getting penalized. And if you take one element and move it one entire page length down, you get a score of 1. So that's why I think of it as a percentage. So web performance, how do we go about measuring this? We can measure this directly from the browser. It's a lot easier to measure performance than it is to measure errors, because performance is a much newer concept. We care that things are running faster much later than we cared when things were broken. And so the APIs to do this are a lot easier. We just need to write a very small agent. This can be a little bit of code in your front end. It could be a standalone thing. It could be built into your app. It could be a third party, whatever. And it doesn't really need to do much. It essentially just needs to call an API called performance. Performance.getEntries is basically everything that you need. All of the timing information that's available in Chrome DevTools about how long every request took and all the different phases, that's all available to us programmatically under the Performance API. Performance.getEntries has every single request that was made and how long it took and all of those sort of things. There's a secondary API called Performance Observer that we also want to capture in case we want to capture those core web vital measurements. But they're both very simple to gather. Once we have that data, it doesn't need to be anything complicated, but we just need to get it out of our web app and start sending it somewhere. So it could be that same sort of custom logging API that we built into our system. Again, Kibana is fantastic at that if you have your own custom data storage that you want to keep. Here's some charts that I have in my Kibana about like performance metrics that I've taken from my client-side applications. Alternatively, there's a number of tools available in this space. I think most of them were really bad, and they were really complicated, and they cost a whole lot of money. And you needed a full-time person to manage how to get anything out of it. So I started building something to try and fix that recently called Request Metrics. I might be biased. I think it's pretty cool. Again, we try and do like really highly opinionated charts and plain English words about like, hey, here's what we think is important and how you're doing and any interesting things that are happening. But let's look at some real web performance problems and how they can impact our service. So for example, the first kind of problem is an overall slowdown in page load time. For example, we're seeing a lot of users have slow performance on our checkout page of Minnesota Ice. There's a lot of users, and they don't all have the same experience. Unlike error tracking, where if we say, hey, we have an error, that's an interesting thing to look at. One error has everything we need. Performance is statistics. Performance is about like, hey, I have 5,000 requests, and I need to look at the distribution of time over them and see if that distribution of time is changing. And so a lot of those kind of performance tools will have charts that look like this. This is a flame chart. And each color of this chart represents the performance of a whole bunch of users. And so the hotter this chart, the slower it was. The trouble is that there was actually a really important slowdown in this chart that is just really hard for a human being to see. Because these kind of charts are actually not good at spotting subtle changes. So instead, it's important to graph the performance of the users, important to see the performance experienced by a group of users separated into different chunks. So hold on a second, I'm going to have you channel that 6th or 7th grade statistics class that you probably slept through. So this is a load comparison report in Request Metrics. And the things that we show here are medians and percentiles. And if you don't remember from that class what these things are, is if you take every single person's performance who visited this page, so everybody who went to the checkout page, I grabbed how long it took for them to load. And we sort those performances from fastest to slowest. Now the median is if I go through those things till I get halfway. Halfway through the performance is the median performance. So how fast did they load the page? And the median here is saying that they loaded the page in 2 to 3 seconds before, but then it started slowing down to about 4 to 5 seconds. That is the score that half of my users experienced that or better. The next part is around the 75th percentile, which is the same thing. So I have that same list of performances. Now if I go up to 75% of my users have that score or faster. The 75th percentile is the most common measurement most people use in web performance because it represents how most people have experienced your site at this speed or faster. It's how most tools will measure it. When you get one score in like a Lighthouse report or a PageSpeed Insight report, like it's usually measuring the P75 of how things came to you. When Google decides on how to penalize you or reward you for your core web vital metrics, they're using the P75 value of your site to determine how you're doing. And in this case, it's slowed down from about 5 seconds to about 10 seconds in this time slot. And the 95th percentile, which is the same thing, we go all the way up to 95th. And the point of that is to understand what is the worst experience our users have. We record that at the 95th. Some people record at the 99th, but you don't record it all the way at the end. Why don't you record it all the way at the end, Todd? That's not the actual worst performance. Well, data on the web is really, really, really noisy. And if you actually record the slowest performance report that you get from a user, on any site of decent traffic, it's going to say something in the terms of years, which is just crap. Like, it's like the site hasn't even been online for 5 years. How did it take 5 years to load the page? And there's just a lot of garbage clients on the web that sends weird data to you that is not correct. And so we always lop off the last some percent of the data to be realistic. We say, we're just going to throw that stuff away. We don't think it's real. And so that's what we think of at the 95th. And so in our case, we slowed from 10 seconds all the way down to 20 seconds. This is the same data that we report, that is charted here in this flame chart. That is really hard to see anything going wrong. But if we break that data down, it is really easy to see that on or around April 1st, everything got slower for every single class of users. And in the case of that 95th, they're now waiting almost 20 seconds to load the checkout page. 20 seconds to load a page so that they can buy ice. I think they're just going to the freezer and getting regular ice if you're waiting 20 seconds. Nobody's going to wait that long. So the checkout page is obviously slowing down. And that's a really big deal for Minnesota Ice, which makes money off of people buying stuff from them. There's a lot of different reasons it could slow down, and we don't necessarily know that. Usually it's things like more or slower third parties that have been integrated in the site, or too much JavaScript that's been added, or hosting issues. The servers that they're hosted on have just slowed down. Hopefully, your tooling can give you better clues on what exactly that is, but we do know that it did slow down from the user's perspective. So if all of your other charts are saying, hey, everything's good to go, I don't know what's going on, you're missing something. Because to the users, they're now waiting up to 20 seconds to load a page, which is unacceptable. So let's have a look at another example. As we talked about a little bit before, in today's websites, there's lots of different ways that a web page can be slow. And one way it can be slow is through that layout shift thing we discussed. We measure this experience, the amount of the degree to which a page moves around while it's loading, in that metric cumulative layout shift. And so Google gave us those values of what good, improve, and poor ranges are. And we can track that over time. And so here's some tracking of one of our pages and how it scored over time. And so most of the days, our P75 value is good. Google's not going to penalize us. But previously, we had almost all good days. And now we have a bunch of days that aren't so good. And we can see all kinds of users are having a worse experience on that shopping cart page. Now, it's not necessarily enough that Google's going to penalize us yet, but it's in the danger zone. Usually, this sort of problem is caused by asynchronously loaded content. So somebody probably added a widget to the page, some sort of third party that renders in an ad, retargeting, something. And they didn't specify how big this image was going to be, or how big this thing was. Okay, let's move on to the third component of client-side observability, usage analytics. Usage analytics means measuring the user traffic, movement, and actions through web pages. And it's super valuable for everybody involved, not just the marketers, because it shows us how our people are actually using the websites that we built. And it shows us whether or not the other things work well. Usage analytics is probably the easiest kind of agent to add to your site. It literally doesn't do anything except give you an API to say something happened. You just need to reveal an API of send event or equivalent. It's like, hey, something happened. And that thing was of this category or worth this amount of money or whatever it is that you think is interesting. This can be something that you build or an external module or whatever. This agent usually just provides a JavaScript API, and that's all it ever needs to do. This can be, again, part of your logging and metrics API. I've used Kibana to track my own custom analytics here. There's also tons and tons and tons of tools in this space that I'm sure you're familiar with, Google Analytics being the big one, but there's Fathom and Cloudflare, and I think there's one built into Azure now, and there's tons and tons of analytics tools. I don't make one yet, so. But they're all super important because they help us answer a single question. Is this acceptable? Is the current state of my application acceptable? Is this error rate okay? Is this performance okay? Is the user able to accomplish the things that they need to do? And how does it help us answer that? It answers that with a concept called a funnel. How many of you have heard of the funnel? Okay, so this is going to be a very brief marketing class. The funnel is a concept in analytics that we use to figure out how effective our stuff is. And it's super easy to think about. The funnel is we have a bunch of traffic coming in the top, starting some flows, starting to do something. Some of the people will finish that funnel. They'll do the thing we wanted them to do, and they'll be the completions. It's like how many people converted, how many people bought the thing, how many people checked out their shopping cart. Others will abandon out and not finish the thing we wanted them to do. And measuring the percentage between those two is basically all we're doing. How effective are we at doing the thing we set out to do? Let's look at an example. The checkout flow is super important for Minnesota Ice, as it is for all e-commerce retailers. It's comprised of the checkout page, and that integration with Stripe, and a server-side call to the order service. So let's look at how analytics will figure this out. If we define our funnel as all of the traffic that comes to the checkout page, so all the people who start the checkout flow, the other steps of the funnel could be things like entering their payment method or providing a shipping address or selecting a shipping method or whatever else is in that checkout flow. Today, about 25% of the people come all the way through and complete their purchase, which is better than average for e-commerce. The rest abandon their cart. They say, I don't want this ice, it's too expensive, or they just never finish for some reason or another. And so knowing this baseline metric is important because it allows us to evaluate when things are acceptable when something changes. So that's pretty good. When something changes, though, like say the checkout page slowing down, recently we saw that the checkout page used to return in 4 seconds for the 75th user, and then slowed down to 10 seconds for the 75th user, or 20 seconds for the 95th. And so we can look at that change and we can be like, oh, you know, that's not good, but I got other things to do and I'm not going to spend my time fixing that. Usage analytics can inform that decision. It says, is that okay? So I can look at the time range and say, okay, when it was 4 seconds, I had a 25% conversion rate. 25% of the people were giving me money at 4 seconds. But if I go back and look at it now, if my conversion rate had gone from 25% to 18%, that's interesting. It's just a correlation. We don't necessarily know that one thing caused the other. But if it was my money, if I was in charge of it, and I was like, we just lost a whole bunch of conversion points to this slowdown, I would be spending a whole lot more of my time and my money to figure out why did that slow down. I would say this is the user saying that that performance degradation was unacceptable. And not only that, if we could make it faster than that 4 seconds, our conversion rate might even go up. So there's a lot of great information that we can get from error tracking, performance monitoring, and usage analytics. But obviously, there are some limitations, and I want to discuss some of them. I've alluded to a few of these already, but the first and most important is that the client side is super noisy. If you're monitoring your server-side applications, every message, every error, every alert is potentially something real and something interesting. If an exception is thrown in your server, that was probably a real exception that really happened. When you get an exception from the client side, it's a 90% chance it's garbage, and it's not real, and you don't need to worry about it. Because the web is so noisy, there's so many different kinds of clients. There's people surfing on their old Game Boys or on their Samsung refrigerators, and you never built your site to work on a Samsung refrigerator. Who tests that? But these things are out on the web, or there's bots that are pretending to be these things, and they will send you data. And so solving the noise problem is one of the hardest things to do when you start getting into this. And it's usually about filtering things down and saying, okay, tell me about errors when 3 users or more have experienced it. I don't care about 1, 2 is kind of interesting, 3 is, okay, this is a real thing that I actually care about. Often you'll see errors that, you might get 10,000 copies of an error that all happen to a single user. Well, you don't really care. This is also the same reason why we use the 95th percentile when measuring performance, because a lot of that statistics that we get is just garbage. The second part is around data privacy, because observing our client-side behavior often has to be balanced against user privacy. We cannot collect everything that we would ever want to know without violating laws, like the GDPR. There's certain things that we simply cannot capture about our client-side environments without having to go full, tons of I accept dialogues as the user comes in, which is just a crappy experience. The user doesn't want to necessarily give up all of their privacy just to browse your website. And so when they don't, you can't capture everything you'd want to know. The third, networks and geography. People are going to be accessing your website from all over the world. And so if your performance slows down, but you also happen to get a whole bunch of users from outer Mongolia, that might not be important, unless you're serving outer Mongolia, in which case that's super important. But knowing what geographies you are trying to serve and measuring the performance for them, and not necessarily anybody else, is important. So today, wrapping up, we talked about client-side observability and how it gives this user-centric perspective of how our application works. I argue that, in fact, it is the most important part of your system that you should be observing. We talked about error tracking. We talked about performance monitoring. We talked briefly about analytics and the funnel. I spend a lot of my time talking and thinking about this topic. Most of my ideas are codified in the things that I build. So if you're interested at all in those, that's at Track.js and Request Metrics. And if you happen to be in the area, you should come to PubConf on Saturday. We're going to have a bunch of beer and funny speakers and whatnot. Thank you so much for coming to Observable Web Applications. I have a bunch of stickers on the back. If you take a sticker that comes with a green card, you don't get one if you put a red card in. Thank you so much for coming. If you want to chat, I'll be up here for a while until the next speaker kicks me out. Thank you so much.